So, good morning to all of you students, and please see this. In this lecture, we are going to discuss this overhanging beam. This is the overhanging portion BC, and no vertical loads are acting on this beam. Only one moment of 120 Newton meter is acting. So we have to plot the shear force diagram for such types of beams. So let us start today. So this is the beam I am drawing here. So this is the beam, and this beam is a overhanging beam, right? So this is first point. I am abbreviating it as A. This is point B, and this is point C. So reactions are acting at these points. So I can call it as, this is the reactive force RA. This is the reactive force RB, and this is the overhanging portion BC. So RA and RB, these are the two supports. Span is 2 meters. Here the span is 2 meters. No vertical load is acting on this beam. Only one moment you can say, and the magnitude of this moment is 120 Newton meter. It is acting over this. If you will look practically, such types of cases arises in case of balconies. So our balconies are like this, right? Now let us start. First of all, our aim is to plot the shear force diagram for such types of overhanging beams. To plot shear force diagram, first of all we have to determine the reactions. While determining the reactions, you have to use equations of equilibrium. Summation of Fy equal to 0 and summation of moment equal to 0. Means sum of all the vertical forces about any point equal to 0, and sum of the moments about any point because of all the forces acting on the beam will be equal to 0 if body is in equilibrium. So horizontal forces are generally neglected in case of beams unless and until inclined forces are not acting over it. So in this case there is no question of horizontal forces, but vertical external forces are not acting, but vertical reactive forces are acting on this beam. So if you will apply summation of vertical forces Fy, this is x, this is y direction, and upward forces, if you are taking positive, downward forces negative, so that is equal to 0. The sum of all the vertical forces about any point equal to 0 as the body or the beam is in equilibrium. So RA is acting in upward direction, RB is acting in upward direction. So you can write here RA plus RB equals to 0. So this is your equation number 1. Now you try to apply summation of moments about any point you can consider, either A or B or C. Solution will not be changed. So I am considering moment about point A and moments about point A because of all the forces, and I am considering clockwise moment as positive. So let us start this RA reactive forces about point A. I have to calculate the moments. So RA is passing itself through A, so there is no lever arm. So RA will give 0 moment. RB is acting here and the lever arm from point A to B is 2 meters. Now you move your pen in the direction of force about point A. See this movement. You will find that this movement is in anti-clockwise direction. So anti-clockwise, negative. If you are considering these conventions anti-clockwise positive, clockwise negative, the solution will not be changed. You can assume your sign conventions as per your wish. So here I am considering this anti-clockwise moment as negative. So quite obvious that the reactive force RB is to be multiplied with distance or lever arm 2 meters. Then RA is over, RB is over. This moment is acting at point C, but this moment will also give effect on point A. Don't think like that. This moment is acting at C. We are taking moments about point A. Why should we consider this moment? No. As this moment is acting in clockwise direction at C, it will give effect on A also. But as the moment is already in Newton meter, you need not to multiply by lever arm. You have to multiply force with lever arm to determine moments. But in case of moments, you need not to multiply with any value or lever arm or distance like this. So this is clockwise moment. So clockwise positive. So I am taking here 120 positive equals to 0. So equation number 2. So there are 2 equations and 2 unknowns, RA and RB. So solvable. So RB equals to you take minus 2RB to the right hand side, so it will be plus 2RB. So RB you will get 60. As we are following the units Newton, it will be 60 newtons. So RB is 60 newtons, and if you will substitute this value in equation 1, you will get RA as, you substitute 60, it will move to the right hand side, so you will get minus 60 newtons. So in this way you have determined the reactions. Now the problem is this RA you are getting minus 60 newtons. So minus 60 means our assumed direction is wrong. We have assumed the reactive force during calculations in upward direction. As we are getting minus 60, so it is obvious that you have to apply in downward direction, right? Because value is changed, it is negative. So I have changed the direction. RB is 60, so it's okay, no problem. So I will substitute now here the values of RARB. This is 60 newtons in downward direction, and this RB is plus 60 Newton, so I assume direction is correct one. So 60 Newton as it is, I have mentioned. In this way, you have determined now the moment, the reactive forces of the beam, and this is the first step, that you have to determine the reactions first. In your higher semesters, this whatever we are plotting the shear force and bending moment diagram in this mechanics of solid, it is for the determinate structures. You can easily determine the reactions. In upcoming semesters, you will come to know that it is very difficult to determine the reactive forces. Unknowns are more than the available equations. Few other methods has to be adopted, employed, in order to determine the shear force and bending moment diagram. That you have to do by other methods. So note this, whatever we are plotting here, shear force and bending moment diagram, it is for the determinate structures only. Now let us start the shear force diagram. You know the sign conventions for shear force diagram. This is your section. In all my numericals, I am following the same. You can assume, take different sign conventions, but follow the same throughout the numerical. So section left, shear force, upward we are taking positive, downward we are taking negative, vice versa to the right of section. So upward we are taking negative and downward we are taking positive. So in this way we are calculating the shear force diagram. Now take first section XX, as I have already explained you. D stands for dead end. You assume dead end here. This is X. And one more thing, you please observe that you have taken at distance X because section left only one reactive force is there, section right one reactive force, one moment is there. So better to take from left hand side. Now you try to develop, I am abbreviating shear force as V. So shear force master equation I am trying to develop, Vxx is equal to the left it is in downward direction, section left downward minus, so it will be minus 60. Now this section is valid from A to B. This section is valid from A to B, and when the section will reach at A, X, see when section will move in this direction, the value X is variable, it will go on decreasing, and at A it will be equal to 0. You try to imagine. When this section will move towards right, this X value will go on increasing. When it will reach at B, the value will be 2. Now you try to calculate at two different points the values of shear force. First of all, you try to calculate at A. Remember, when we are determining the shear forces, no need to multiply force with distance, because shear force is force itself. In moment you have to multiply with distance. So VA 0, we cannot substitute here 0 value because there is no X variable where to substitute. So VA will be minus 16. Then you try to calculate VB. So VB you will get, again you cannot substitute this value 2, no variable is there, so it is minus 60. So from this master equation you have obtained the shear forces at these 2 points. Now proceed further for the second section, and the section is x1. Now this time I am taking this section from right hand side, dead end C, because if I will consider the left side, there are 2 reactive forces, so better I have to consider from right hand side. Now your master equation x1 will be equal to what? This is the big question mark. To the right of this section x1, no vertical force exists. So if I am considering the right hand side of this section, there is a moment but no vertical force. So the master equation is 0. No doubt the section is valid from C to B, as I have considered section right. And if it is reaching at C, it is equal to 0. If it is reaching at B, it is equal to 2. So the shear force at C is equal to 0, and the shear force at B will also be equal to 0. So in this way you have determined the shear forces from these 2 master equations, and now it's time to plot. When we plot, my sign conventions are, I used to plot the positive values above this horizontal line and negative below this horizontal line. So this is A, this is B, and this is C. So start with this VA. So at point A, you are getting minus 60. Minus 60 means it is below. This is this. VB minus 60. So at point B, negative values, I am plotting below this line. So minus 60, same ordinate. I am getting like this. I will join this with straight line. In my previous lecture, you can listen carefully my lectures. Unless and until the degree of the equation x square, x cube is not here, you cannot plot the curves are like this. If you are getting 2 minus 60x square, if you are getting suppose in different types of loadings, then you have to plot and join the points with second degree curve. Here it is not so. So you have joined with the straight line, and VC VB is 0. So again this VC is 0, and from second master equation VB is also equal to 0. So you have to come again here, VB equal to 0, and then draw the straight line. So in this way the shear force diagram is plotted. So students, the shear force diagram which I have plotted here, you please have a look on this slide. This is your numerical, right? And in this way the shear force is plotted. So I think that the concept of shear force is clear to all of you today. In my next class I shall try to plot the bending moment diagram. Few more numericals we will discuss. Thank you very much students. Thank you.